like scary big, just important big. So I'm hoping that you are wide awake, ready to go, ready to jump in and do physics today. Last time we were together, we did a lot of important things. We're going to build on that today. I would say that, yes, last time and today are kind of two of the like big fundamental we need to understand this days for chapter 4. Okay? You got to get this stuff. I am recording this, so if you want to go back and watch it because you don't remember everything, you're always welcome to do that. I just want to make sure that we're here. So last time we were together, we wrote down what I fondly call Newton's first and second law, right? It's one law, it's one rule with two kind of cases. We decided, based on watching that bowling ball roll across the floor a couple times ago, that if the net force acting on something was 0, what do you know about the object's motion? What equals 0? Something equals 0. Acceleration equals 0. So it's moving or not moving, but either way, it's not speeding up, slowing down, or changing direction. Does that make sense? Okay? If F net is 0, A is 0. We also said if F net wasn't 0, I mean, it kind of makes logical sense. If it's this, then we know that. If it's not, then it's not, right? Okay? If the ball is yellow, then it's yellow, and if it's not yellow, then it's got to be some other color besides yellow. Does that make sense? That's what we're talking about. So if F net is not 0, then A is not, acceleration is not 0. Speeding up, slowing down, changing direction, we don't know. But we know that it's not at a constant speed. Okay? We did not tell anything more about what acceleration is. That's where we need to start today. Okay? So I'm going to extend. Did I suggest maybe that you leave a few lines right under that? Wow, that was me thinking ahead there. Good for me. Good for you. Yay. You have a couple lines. I don't usually remember to suggest that, so I'm glad that I did suggest that to you. All right. So if F net isn't 0, then A isn't 0. We want to know what A is. Because in physics, we like to describe the world and we like to describe what's going on. And we like to describe it as accurately as possible and as specifically as possible. And just saying it's not 0 is not super helpful because there are a lot of choices that aren't 0. Okay? So I want to know how to find or what affects the acceleration of an object. What affects the acceleration of an object? Any ideas? What may change how much it speeds up, slows down, or changes direction? What do you think?
The amount of force applied to one object.
Does that make sense? The amount of force? So if I have a bowling ball, for example, and I want to accelerate it, you know I have to apply a force, right? We said that earlier. If I apply a little force, it's going to accelerate. If I apply a big force, what do you know about its acceleration?
It's going to be larger than small.
It's going to be larger. Does that make sense? Does that seem like a logical thing, right? If you push on something a little bit, it's going to go a little way. If you push it, it's going to go more. It's going to accelerate more. Sure. So let's say that. So F net, the net force, definitely affects the acceleration. If F net goes up, we can say that the acceleration is going to go up. That seems to make logical sense. What else might affect the acceleration? Let me pose it. Oh, yeah, go ahead.
The mass.
What'd you say?
The mass.
Tell me more.
Like something more massive takes more force to accelerate.
So-
like if you apply 1 Newton of force to a less massive thing, it'll accelerate faster than a more massive thing.
Does that make sense to you guys? Can you kind of picture that? Yeah. So like, let's think about let's push 2 different balls, right? Or maybe I don't want you to hurt yourself. So make sure you're wearing good shoes in your imagination here. And imagine that you're going to go up and you're going to kick a ball, okay? And you're not really paying attention to what the ball is. So you're going to apply the same force, right, like the kicking force, your foot kicking force, either to a soccer ball or to a bowling ball, okay? Are you going to get both of them to accelerate?
Yes.
Yeah. Assuming we're not hurting our foot, right, we want to ensure safety. Which one is going to accelerate more? Soccer ball, bowling ball? Soccer ball. Soccer ball has less mass. So that means if we're going to put that into a statement kind of like this one. As the mass goes up, what happens to the acceleration of the object?
It goes down.
It goes down, right? Logically that makes sense, right? Again, this is not something that it takes a genius to figure out. You're all smart, so we can figure it out pretty fast, right? But let's be honest. This concept right here was probably something that cave people knew, right? They had to move big boulders. They knew that if they had more people pushing, more force, more acceleration, yeah? Right? Okay? They knew that if they had more mass, it was going to be less acceleration, right? This is not something it doesn't take a lot of, deep thinking to figure this out. Do you agree? Okay? So even though we attribute all of this to Sir Isaac Newton, la-di-da, okay, we've known this for millennia before him, right? I'm not trying to sell him short, but let's be honest. That's not that hard. Okay, so if we're going to put this into a statement, it's really just these two things that affect the acceleration. If I want to make a statement for acceleration, and I want one thing to go up, the other one goes up, I'm going to put it in the numerator. Does that make sense? So I'm going to put F net up here because as this one goes up, I want this one to go up too. It's in the numerator. Are you with me here? Yeah? As this gets bigger, this is going to get bigger? Anna, you're looking like I'm a little crazy. Yeah, you are, just a little bit. Let's be honest. Is that okay? Do you understand what I'm saying? Or do you want me to say more? Okay. She's like, I'm not going to look at you anymore. No, I don't. Okay. I just want to make sure I wasn't sounding crazy. Sometimes I do. I'll admit it. As M goes up, we want A to go down. Are we going to put that in the numerator? No. Where do you want to put it? Right there, right here? In my, some distance away? What do you say?
I want to pick denominator.
Where's it going to go? Denominator, right? M goes down here because as the denominator gets bigger, the total thing gets smaller, right? We know that. We love the fractions, okay? This right here is an important statement. That would be worth putting a box around, maybe some stars next to exclamation marks. If you use highlighters and gel pens, this is where you use them. This is an important thing to pay attention to, okay? This right here is the second little piece of Newton's first and second law, okay? So not only if F net isn't 0, then we know that A isn't 0, but we know that if F net isn't 0, then we can figure out A if we know the net force and the mass, okay? If we know the net force and the mass, we can find the acceleration. So we don't just say, oh, it's not 0. Now we can actually tell you what it is. Okay? Is that okay? Okay. Sometimes we rewrite this because people get scared of denominators. I don't know if you guys are all scared of. Hopefully you had good elementary school math teachers, and so they didn't freak you out about denominators. Sometimes people are scared of them. I've kind of decided I want to dress up as a denominator for Halloween sometime. I haven't yet figured out how to make that costume happen. So if you have any ideas, right? And a number up here, I feel a little like somebody on Sesame Street. I'm not really sure, but people be like, oh no, denominators, right? I don't know what the deal is. People just get freaked out for some unknown reason. But anyway, sometimes we'll write this instead this way. F net, we multiply by M because then we don't have a denominator. Oh no denominators. And we'll write it like this. So we'll say that the net force is equal to its mass times its acceleration. I have a strong preference for this one up here, the green one, because this is the effect of this cause. It's a cause and effect statement. doesn't have denominators. Like, I think that's the purpose of that one. Okay? Are we okay with that? Okay. So, I'm going to come back to a problem we were working on last time. We were working on these normal force problems. Do you remember this? The frog on the right, yeah. So we had the frog. I just want to kind of get our brains back into this because it's been a few days. We're talking about a frog sitting on a table. There he is. Sitting on a table, and he was happy. Okay? And in doing so, we knew that there were two forces that were acting, and we could find the magnitude of the force, of the normal force. Normal means what, by the way?
Parallel.
No, wrong one. Perpendicular. You were so close, yes. Good job for saying something, though. But yeah, it was the other. It's the perpendicular, right? Normal means perpendicular. It means that it is acting perpendicular to the surface. Going to keep that in our brains because it's important. It's going to matter today especially. Okay? So the normal force was this. Then I decided to take my frog on a walk because he does need daily exercise. So I took him on a walk. And I asked you to find the normal force again. And I think this is about where we ended last time. Is this right?
Yeah.
Does this look familiar? And the big deal thing that we figured out, and this is really quite important, is that the normal force is not the same now as it was before. The normal force is dependent on the situation. It's not always going to be equal to the force of gravity. How did it change? Did it increase or did it decrease? It went down, right? It was 4 and now it's 2, so that went down. Why did the normal force go down? Why did it go down? What'd you say, John? Yeah. You want me to go all the way up? And then go back down? Just like to watch it move. Whee, it's fun. Why? Why does it change? Why does it go down?
Wait, I'm confused.
Yes, ma'am.
When it says mass of gravity, wait, is that what it means?
Where are you looking at?
mg, whatever mg is.
mg here.
Yeah, is that 9.81?
The g is 9.81. So m times g is the force of gravity, which is the mass times the acceleration. Does that make sense?
And that was 4.4 from the...
Yes. Yep.
Oh. Oh, okay.
Does that get you where you need to go, hun?
Maybe.
Okay, let me know. What you got?
Because it's like, because of the least, you're like just being pulled on something, so you have to subtract another number. So
Yeah.
FAY.
Yeah. Yeah. If we add up all of the forces that are pointing in the up and down direction, what do they have to add up to? 0. Why 0? Because there's no acceleration. I'm going to just bounce this back right up here for just a second because I want to make sure this makes sense. He's not accelerating in the up and down direction. Do you agree? In fact, he's not going anywhere in the up and down direction. If he's not accelerating, we know that the F net has to be 0. Is this okay? Is this making sense? F net has to be 0. So then if we go back to the picture, that means that all of these arrows that are pointing up and down have to add up to 0. In the other picture, we only had these two. This one wasn't there. So these two had to be equal. Now we've got 2 arrows pointing up, which means that this one's got to be a little smaller. Is that sitting okay with you? Okay. We really only looked at this problem in the y direction. We didn't talk about the x direction last time, and I want to do that right now. Okay? I don't remember what I told you last time about whether he was accelerating or not. I want you to look carefully at the picture we have drawn. If, excuse me, if we have all of the forces drawn that are acting on the frog, is the frog accelerating? Ashley's shaking her head. Can you tell me why you say that?
It's accelerating in the x direction.
Why?
Because there's only one pointing in the x direction, so there's like nothing to make it 0, so it has F net thing.
Does that make sense to you guys? Yeah. There's only one force, and if there's one force, then that one force can't add up to 0, right? That's what she just said. So if you got one force and it doesn't add up to 0, because that doesn't make any sense, then he's got to be accelerating. I would like you right now, with your partners, a little challenge for you, I would like you to see if you can figure out what his acceleration is in the x direction. Talk to your partners, see if you can figure out what to do. Have a little conversation. We'll go through it in a minute, but I want you to see if you can do it. Go, go, go. So if you were not sure what to do, then make sure that you're playing with me now. Okay? If you were sure what to do, or you think you knew what you're supposed to do, check it and make sure that what you're doing here matches. So the way that we approach these problems, friends, is always to start with a free body diagram. We have that done. Check. And then write F-net equations down. Which direction do we care about right now? The x. So we need to write down an F-net equation in the x direction. So F-net in the x direction. Then I'm going to say, okay, well, according to my picture, what forces are acting in the x direction? Are there any forces acting in the x direction?
Yeah.
How many? 1. What's it called? F what? Somebody over here said it. What did you say? I'm looking at you. I won't look at you. What did you say?
FAX.
FAX. Is it? Am I scary? Do I have like laser eyes? I don't know. So FAX. Everybody okay with that? Is one force going to add up to 0? No. We know that it's accelerating. So we're going to go back here. We're just going to make sure that we're not talking crazy talk. Oh, well, if there is acceleration, hey, look, F net is going to equal ma. So let's just write that down. Here we go. So F net is going to equal ma. Is that okay? Okay. I'm just putting the stuff together that we've talked about. I'm not trying to do anything else that's scary. We can find that A, or that force, excuse me, because we know the applied force was 2.5 newtons, and it was at an angle of 65 degrees. So can I figure out what FA in the x direction is? And Marie's like, yeah, how do you do it? Yeah, we're going to use some sort of sine, cosine, something, right? Let's figure out which one. What part of the triangle is this? Hypotenuse. What part of the triangle is this? Adjacent. Is everybody okay with that? If you don't remember this off the top of your head, you can always look back at your equation sheet, that purple sheet. Adjacent, hypotenuse, which one do we use? Cosine. So FAX is going to be FA cosine theta. So if we plug in numbers there, it's going to be like 2.50 times the cosine of 65. Oops, I guess I need another parenthesis there. What was the mass, like 5 or something? 40.45. That's what I meant to say. 0.45, 5 kilograms times acceleration. Can you find the acceleration then? Yeah. What do you got? What is it? 2.3? 2.3 what? Boom. You got it. Is that okay? What questions do you have about that? Yeah.
I put that in my calculator and I got the number.
Yeah, you got the crazy calculator. It probably is using radians. I would borrow one of mine or talk to somebody who knows what they're doing because I don't. All right. Are we okay here?
Hold on.
Going once. Going twice. Can I move on? Not quite yet. I see some pencils moving. Okay. This little page says trio of normal force problems. We've done 1, 2. That means we've got one more to do. Last situation. This situation says to determine the normal force acting on the frog, same frog, while he is sitting on a ramp with an incline of 25 degrees. So this is the situation, my friends. Take a look up here. I've got a ramp sitting at 25 degrees. He is at rest. Okay? I want to know the normal force. Does that make sense enough so far? Okay. We are going to draw this free body diagram. You need to draw this free body diagram. You need to draw this free body diagram very large. Whoosh. Okay? So at least, like, I don't know, 5 lines of your paper, and at least, like, half in the width. Like, it's going to be a big picture. And the reason for that is because if you draw it little, it's going to be really confusing. I promise. Because I've done this a couple times. Okay? So, you can kind of follow me through this drawing process. You don't have to get a protractor out, but we're going to draw some sort of ramp like this. And we're going to put the frog on the ramp. The question, or at least the one that's written in here, asks for the normal force. So we're going to start there. But we know that whenever we're trying to solve for any forces, the very first thing that we should do is to draw a picture. And that's a nice picture, but we need to add what to it in order for it to be a helpful picture? Some forces, right? So we're going to do this together. You may want to do this in pencil if you're not writing everything else in pencil, because this one, it gets a little bit tricksy when you draw it, and I don't want you to have to, like, start over 7 times. All right. Let's think about what we know. What's acting on the frog? Raise your hand if you can tell me something acting on the frog. I want to share my fun with lots of people. So put your hand up. If you don't usually talk to me, this would be a good time, because this is a great opportunity to share. Rowan, what you got? Force of the earth, right? Where is the force of the earth pulling or pushing? Where's it going? Down. It always goes down, right? Yeah. So we're going to go ahead and draw it. I want you to draw it pretty large. A big force of the earth. Force of the earth on the frog. And in parentheses, we're going to say, oh, wait, that's what kind of force? Gravitational. So I'm going to put that in FG in parentheses so that when I start writing my FNet equations out, I can just write FG. That just makes my life a little easier. What other forces are acting on the frog? What else you got? Think about what else you know. Sean?
The ramp.
The ramp. The ramp is a surface, would we agree? And we want to be very careful here. We're going to look here at our list of forces that we know. We talked about gravity, we got that one. Are you maybe implying that we've got a normal force? Is that what you're kind of talking about, or no?
I don't know.
Which way do you think the ramp is pushing? Not trying to put you on the spot, I'm just asking.
Oh, up,
Up where? Up what?
up.
Like straight up towards the sky?
No. Like.
Didn't he point up when I...
Oh. Perpendicular to the surface.
Oh, okay, now he's changing the story. He says perpendicular... What made you change your story?
Because last time we talked about how normal force is perpendicular to surface.
Right. Does that make sense? Yeah. So remember we said last time, and it's kind of a weird thing, so I want to make sure that we're kind of sitting okay with this. A normal force is a surface pushing on an object, and it's going to push on the object perpendicular to that surface. It's not going to push it like this, because if it was, like, think about that. If I put my frog here, and my hand was pushing like this, then he's going to go that way. Does that make, you see what I'm saying? Like, does he do that? No, like, he just sits there, right? So it's got to be pushing straight up in this case. But if I tip my hand, if it was pushing straight up, then where's he going to go? go, I mean, it's just logical. I mean, I don't mean that in like a snotty way. I mean that in just like an honest way. It's got to go this way, perpendicular to the surface. Are you with me there? Is that okay? So, Sean, you called that the force of the ramp? Is that what you said?
Yeah.
Okay. On the frog. And in parentheses, I'm going to put Fn. Now, we've got a little thinking to do. Are these two forces going to cancel each other out so that the frog doesn't move?
Hopefully.
No.
Are they going in exactly the same direction?
No.
No, not quite. Because this one's going straight down towards the center of the earth, right? The gravity? But the normal force is going perpendicular. Are you with me there? Okay? So this problem is a whole lot like the frog on a walk, where you've got something going at a funny angle. The weird thing about this question is, unlike the leash, the thing that I'm going to call going at a funny angle is gravity. Gravity seems like this basic normal thing that we understand, right? Like, my 2-year-old has understood gravity for like a year, right? Like, you take something, you let go, oh, it's going to fall, right? Like, we know this. This is not a surprise. You guys have known this for a lot of years, okay? But in this case, do you see what I mean? Like, this is easy. It's perpendicular to surface. This is like at some crazy town angle. Are you with me there? You see what I'm saying? Okay? So what I want to do is take this force, kind of like we did with the leash, and I want to break it into pieces. Can we do that?
Let's see what's going on here.
So this is the best. Maya's got it figured out. She's going to take her head and tilt it. So take your head and tilt it, and then everything is good. So you're just going to walk around like this. Okay? So if you walk around like this, life is okay. This is what we're trying to do. We're going to make an axis where one of them goes like this, and the other one goes like that. Are you with me there? Okay? If we do that, if we make our axis tilted, so if you just tilt your head, then everything is fine. Okay? I don't want to call them X and Y, though. Let me tell you the reason. In the problem we did before, I'm going to go back to the leash problem for a second. It made sense to have things in the Y and in the X, right? That was logical. Here's the issue. My guess is that right now you would want to call this one the what axis? You would call it the Y, don't you? But what happens if I take that ramp that's only tilted like this and I tilt it like that? Are you with me there? And if he still sits there, then this thing that we wanted to call the Y is now really close to the X. And then it just gets confusing. Like, that's weird. So this is what I'm going to suggest. Let's go back to, like, basics, and let's call this axis, the one that you wanted to call the X, let's call it the parallel axis, because it's parallel to the surface. And the other one, we'll call it perpendicular. And then we know for sure, because this one's always going to be perpendicular, no matter how far I open the book. Right? Always going to be perpendicular, always going to be parallel. This is not how it's written in your textbook. I think this is better. That's why I'm telling you it. It's not like I'm going to be like, I'm going to tell you something worse, right? No. I think this is better. I think this makes more sense. That's why I'm telling it to you. So Fn is all in the perpendicular direction. Fg is not. But we can break it down into two pieces. One that goes like this. And one that goes like this. What do you think? Is that an okay idea? Here's the important thing to remember. I'm going to write it down because it's really important. When splitting a vector into components the original vector is always the hypotenuse. When splitting a vector into components, the original vector is always the hypotenuse. So this vector, the original vector, has to be the long one. That means that this angle has to be the right angle. Are you with me there? Okay. Now, this seems a little strange. We're going to practice this a bunch of times. You'll be okay with it, I promise. But it will take a little practice. That's our angle. I'm just going to call it theta. And now we're going to get our mad geometry skills out. Okay? Those of you that had me in geometry last year, you know how much I love triangle rules, right? Yeah? I'm not going to write a proof for this, but we're just going to talk through a thinking proof. So this is like a vocal proof. Are you ready? Is everybody ready? Put your pen in the air if you're ready to go. Show me that you're ready. Up high, above your head. Way up there so I can tell that you're kind of ready. And if you're not quite ready, that's okay. That's why I'm checking. Okay. I see some pens and pencils. Okay. All right, here we go. I've got a triangle right here. Do you agree?
Yes. Yeah.
Yes. Why isn't it yellow? There we go. What kind of triangle is it?
Right.
It's a right triangle. Does everybody agree with that? Because we know that this has to go, the FG has to go straight under the center of the earth. So that has to be a right triangle. So let me get my pink back. There it is. Okay, now, pulling out those geometry skills. If I add up all of the angles of a triangle, it has to add up to how many? 180. You all know that, right? This is not a surprise. Okay. If I subtract this angle off, 180 minus 90 gives me how much left? 90. So I've got this one and this one that have to add up to 90. Life is good? Okay. If this is theta, let me suggest something. Can I call this one 90 minus theta? That angle there, is that okay? That's not wild. That's not too crazy, is it? Like I'm not totally messing with your heads? Okay. You're like, whatever, that's really okay. Just want to make sure. I'm not trying to dumb this down. I just want to make sure it makes sense. Okay. Talk to me about this angle right here. What do you know about this angle? 90? Does that make sense? Because this dotted line is perpendicular to this, right? Perpendicular means that this has to be 90. Now, some more mad geometry skills. If I add up the angles on a straight line, they have to add up to what? 180. Everybody okay with that? 180 minus this 90 is going to give me 90. Everybody okay there? So if I've got this thing that's 90 minus theta plus this adding up to 90, what does this have to be? Okay, let's write that down, John. 90 minus theta equals what? Right, but what does it equal? What is 90 minus 90? 0. And then the negative is going to be distributed, right? True? So what does it equal, friends? Yes? Is that okay? So in this case, because this one says that it's 25, then this has to be 25. Now, the reason I like to write it as theta and not as 25 is because then I don't have to go through this every single time I'm doing this problem. This angle here is going to be theta. So let's talk this through. If this was 45, paying attention, what is this going to be? If this is 10, what is this going to be? time forever, so you don't have to write it out every time. You just need to know that, okay? That these two angles will be the same. Life is good? Okay, we're going to keep going. You're like, man, this is a long problem. I know, right? It is. Okay. We were breaking FG down because what's the purpose? We're trying to find the normal force. Oh, right. Finding the normal force. Let's go back to that problem. I want to find Fn. How many forces are acting in that perpendicular direction? Well, this one for sure, right? Is the frog accelerating like that? No. That would be weird. It's not. Which would imply there has to be at least some other force, right? What force is keeping him from going? Gravity. Is it all of gravity that's pulling him the other way? It's just this piece of gravity. Are you with me there? Okay. So let's call that, we're going to call that FG. Well, it's the part that's perpendicular. And we're going to play the same game we just played a minute ago. Well, a few minutes ago now, I guess. This is the what of this triangle? Hypotenuse. This is the what, if that's my angle? Adjacent. So how do I find FG perpendicular? We're going to use cosine. Does that make sense? So this is going to be FG cosine theta. How are we doing? Are we okay so far? Sweet. You guys are doing a great job. I know it's kind of weird and kind of long, but we'll practice this a bunch. We just have to go through it once the long way. All right. Anything else acting in that funny perpendicular direction? Do you see any other purple forces on there? No. So now we can figure out what Fn is. We're going to write down, to find out the force, we're going to write down an F net equation. Which F net do we care about? Parallel or perpendicular? Perpendicular. So I'm going to write F net perpendicular. So I'm doing the same process that I did with the frog on a leash problem, except instead of doing X and Y, now I'm writing perpendicular and parallel. So here's F net perpendicular. Looks like the things that are acting are Fn and Fg perpendicular. Is the frog accelerating in that direction? No, I hope not. So that means that F net has to be what? It does. Are we okay so far? Okay. Can you find Fn? Do it. Do it. Find Fn. If you're still working, that's totally fine. Keep going. I don't want to stress you out. I'm just going to kind of push things in a direction here. Fn is going in a positive direction. Fg is going in a negative direction. So that will kind of push you in the right direction. The mass is 0.45 kilograms still, and theta was 25 degrees. Does this process, I tried to make this as clear as possible, but let me know if it's not making sense. Remember, the vector hats are telling you that it has direction. So I'm applying the directions here. I'm saying Fn is going up. Fg perpendicular is going down in that axis. So I'm going to make that one positive and the Fg perpendicular negative. Okay? They have to add up to 0, which means that Fn is really just going to be equal to Fg perpendicular. The magnitudes are the same. Fg perpendicular is just Fg cosine theta. So that's where that comes from. And we remember from last time that Fg is just mg. So we've got m times g times the cosine of theta. Whew! That's a mouthful. But that will give us Fn. What are we getting for Fn? Did you get a value? What'd you get? 4.0008. You guys agree with him?
Yeah.
What are the units for that? Newtons, because it's a force. And Ashley looks unhappy with that answer. Why?
Can you go through it? Like, do we need some?
Oh, absolutely. We certainly can. And then, yes, that was what I was thinking too. Yeah, so I would just put in, so that's going to be 0.45,
Yeah.
9.81.
Not negative.
No, because I already took the negative into account up here.
Okay.
Does that answer your question? Or do you want me to keep talking?
Keep talking.
Okay, you just got to keep telling me. And then we're going to do cosine of 25. Yeah.
Wait, how do we figure out that theta was 25?
Because it said so.
Oh, it did.
Yeah. It said a ramp with a 25-degree incline.
So m is, how much is away?
M is 0.45.
Okay. How we did that.
Yeah, I went through. I didn't get that answer.
Let me look at your calculator. Okay, show me what you did. Oh, okay. So what you did, what happened is that when you put cosine, it didn't multiply.
Okay.
So if you do that and then hit times and then do cosine, then it will work.
So times cosine.
Yep.
25.
Yep.
Okay.
There it goes. Yeah. You guys doing okay back there? Yeah? So would this answer get full credit? No, because it's got like oodles of sig figs, right? That's 1, 2, 3, 4, 5. How many do we really get?
3.
How many does this one have?
9.81.
Right, but you get as many sig figs as the fewest number you get, right? Yeah. So this one only has how many? 2. So your answer should have. So the answer should be 4.0. 4.0. Whoa! That was cool. Sometimes these, it like gets a mind of its own. It's pretty amazing. Okay. Are we okay so far? So high five to all of you. We solved the problem. But, there's more. There's always more. Zach, you know me. You ran out of room. You better find another page. There was a question that was hiding in here. Do you see the question that's hiding? It's in parentheses. It's hanging out right here. It says that the frog is sitting on a ramp at 25 degrees. If we look carefully at this free body diagram, should the frog be sitting at rest on the ramp? No, I don't think so. These guys are going to cancel each other out in the perpendicular direction. But take a look at the parallel direction. How many forces are acting in the parallel direction right now? One, which would imply that he's going where? Down the ramp. But if we watch carefully, there's a frog on a ramp. Is he sliding down? No. There's something else acting. Are you with me there? There's something else acting. There's something that has to be pushing where? Up. Does that make sense? To counteract this thing, there has to be something going up this way. Yeah? What's that thing called? Friction. Okay? So let's write down what friction is, and then we'll come back to the problem and figure out stuff about friction. So I'm going to go back to the page because I forgot to tell you to save space on this, that lists my forces. But if you didn't leave extra space, we'll just put the force of friction on the next one. Here we go. So the force of friction is kind of a cool force. Okay? What do you know about the force of friction so far? What do you know, or what have you learned? Anything? You've heard the word, because y'all came up with it. What is it?
It's like when two objects are rubbing together and like the whole heat.
Yeah, and it generates, what'd you say? Heat, absolutely. So if you take, I distinctly remember in like 3rd grade, I think, or maybe 4th grade, my teacher teaching us about friction in science class, and this was the first thing she did, right? Did this happen to you or no? No? Right? Like, this is friction, right? Okay, kids, this is friction. The idea being that you've got two objects, the palms of your hands, that are rubbing together. Now, it doesn't have to be palms of hands. It can be frog rear end is what I was thinking, and book, right? Or any two objects. So it's two objects that are rubbing together, or at least interacting, right? So you've got two objects that are touching. Are they actually touching? We don't know. But anyway, sorry, I just had to. Yeah. So this is a force between two objects, just like any other two forces, right? Generally, we talk about it between a surface and the object. Okay? It is a force that is going to slow things down or prevent them from moving. Okay? Depending on the situation, you can have one or the other. So it will either slows an object down if the object was moving already, right? Or prevents the object from moving in the first place. Does that make sense? Okay. If we want to quantify or to calculate the amount of friction, so the friction, I think that I've written this before, so like normal force is like an Fn and gravity is like an Fg. Frictional force is going to be F sub F. Okay. If we want to quantify or calculate the force of friction, what do you think it's going to depend on? Any ideas? What's that? It's going to have something to do with gravity, right? And it's a little bit hard to, like for this to be like an intuitive thing, but it's actually not the gravity of the object, but it actually is the normal force. And the normal force is dependent on gravity, right, in general. Okay? So the force of friction is going to be dependent on the normal force. And what else? Well, that's part of that goes in there. Yeah. What about, you look like you wanted to say something, Abdul. What were you going to say? I couldn't hear you. The acceleration? So, yes and no. So I would say that the acceleration is the effect of friction. Does that make sense? So the friction isn't going to be dependent on it, but it will help determine. Does that make sense? There's one other thing. What if you think about walking with your shoes, whatever shoes you have on, walking either through grass or on an ice rink? You have the same, if you're walking on a horizontal surface, right? You have the same normal force whether you're walking on grass or walking on an ice rink. Is the force of friction the same in those two cases? Certainly not. What's different? The surfaces, right? Now, you may have also experienced this walking on, like, let's say walking on a tile floor with either, like, fancy dress shoes on or dance shoes on or hiking boots, right? Does that make sense? So it's not just the surface you're walking on, but it's also what you have on your feet. You know what I'm saying? So it's a relationship between those two surfaces, okay? And that thing, so we'll call that, it's a funny thing. We'll talk about, let's say, the surfaces in contact. And we quantify that in a very specific way. We quantify that by using this thing called the coefficient of friction. And that's something that you can determine experimentally, okay? The coefficient of friction is marked or denoted by a new Greek letter to us. Does everybody see the thing that looks like an M up there? Okay? That isn't an M because it's a Greek letter. It's the Greek letter mu. Can you say that with me? Mu. Okay, it's kind of like the noise a cat makes. Okay, except we don't usually do it up so high pitched. Okay? And the coefficient of friction is marked with the little mu. So let me teach you how to write it. Are you ready? You're going to start now, like if we go back to like kindergarten lined paper, right? You're going to start below the line. Here we go. You're going to start below the line and come up. I feel like I've never taught handwriting before. It's kind of fun. You make like a little U and then you come back down. Okay? So it's like a small U except it's got this little front tail thing. Okay? That's mu. Okay? Say it with me again because it's fun. Mu. Mu. Okay? Coefficient of friction is marked with the letter mu. And mu is calculated as FF, the force of friction, divided by the normal force. FF divided by Fn. What are the units of FF? It's a force. What are the units of a force? Newtons. What are the units of Fn? Newtons. So you've got newtons divided by newtons. What does that leave you with? Nothing. Mu is a unitless quantity. Which sometimes people are like, well, sweet, that means I don't have to remember units. But it also means that you have to not put units. Because if you put units, then it's wrong. You know what I'm saying? Like, the lack of units is what makes it correct. Okay? So mu is a unitless quantity. Okay? It generally has a value somewhere between 0, excuse me. There we go. And 1. Okay? Sometimes it gets a little bit big, but I would say you can bank on this. Okay? Somewhere between 0 and 1. And we can write then the force of friction, FF, again, just getting rid of our scary denominators, as mu Fn. And I'd put a box around that. There's one other really important thing about the force of friction that I want to make sure you have written down. And then we're going to find out what mu is. Friction acts between two objects, between a surface and an object, but it acts in a very specific way. If you imagine two things rubbing against each other, where do you think the force of friction acts? Do you think it's perpendicular to the surface? It's parallel to the surface, okay? The force of friction always acts parallel to the surface. Which is good because the normal force always acts what? Perpendicular. Okay. All right, can we jump in and try it? Are you ready?
Can you scroll down a little so I can
Of
see
course.
the boxes?
That far?
Yeah.
Yeah. So here's my next question for you. You ready? Like, waiting with, you're like, yes, I really want to know what you're going to ask, right? So excited. I can't believe it. Oh my goodness. I want to know, and this is you have to kind of think this through. I want to know what the coefficient of friction is between the frog and the surface.
Wait, so it always acts parallel to the surface?
To the surface, yes. That's what I want to know. The next question is, what is mu? You say, well, I don't know. What is mu? It's the coefficient of friction. In order to find mu, what are you going to have to find? The force of friction. Any idea where we're going to find that? Go look at Target? Like, where are you going to, I don't know. Let's look up here.
Was there an equation? Did we ever write down an equation for the
We just said mu at then.
Oh,
Right?
oh.
Where's friction acting in this case? Up the hill, right? Preventing this thing from going anywhere. So here we go. Up the hill. This is the force of the ramp on the frog. Are you with me there? But it's not a normal force. It's a what force this time? Frictional force. What else is acting in that parallel direction? Some of gravity, right? Oh no, really? This is not a good time. It's like, whoa. It's coming back. So you want this one here and this one here. You want to make a F-net equation in the parallel direction to find FF, and then using that you can find mu. You have enough information. I'm going to let you try. Give it a shot. I bet you. Okay. So our main goal is to find mu. Okay? Because that's what I asked you to do. I don't know how to find mu. I don't know what mu is. I do know, because I wrote it down a minute ago, that if I can find FF and FN, then I can find mu. Is that okay? You can say no. I just want to know. Yeah, it's okay? Is everybody okay with that? Okay. I already know FN, because I found that earlier. I need to find FF. So this is these really are just puzzles, right? We just have to kind of figure out what we're trying to find and then find it. So my first goal then is to find FF. So I'm going to write down an F-net equation, F-net in the parallel direction, okay? And then I'm going to look at my free body diagram and figure out what forces are acting in the parallel direction. Parallel to the surface. So let's look. What you got? Tell me what something is that's acting in the parallel direction.
FG parallel.
FG parallel, right? It even says parallel in it, so it's got to be parallel. So that's part of it. So we got FG parallel. Anything else acting in the parallel direction? Friction, right? There it is. It's right up there. Anything else acting in the parallel direction? No. If we add up all of the forces, the net force, or if we add up all the forces in the parallel direction, is the frog accelerating in that direction? Yes or no? No. He's at rest, right? If he's at rest, he can't be accelerating, which means that the net force in the parallel direction must add up to what? 0. Okay? Is that okay? Okay. So then we're just going to play the game. We're going to do the same kind of process that we've done the last few times. I know this is new to you. If this is not coming really easily, please go through this again this weekend, okay? I'm going to post this video up. You can just like relive this experience. It'll be fun, okay? You can do this. Is FG pulling in the up, positive or negative parallel direction? What do you think? Negative, right? What about the force of friction? Positive. So this one's going to be negative, this one's going to be positive. So this is negative FG parallel plus FF is equal to 0. Again, thinking about our goal, our big goal is to find mu, which means we have to find FF. So let's get FF all by itself. FF equals FG parallel if we move it over the other side, right? Now, I didn't write this out for you, but kind of like we did with FG perpendicular, can you write a similar thing down for FG parallel? What would you write down for FG parallel? What is FG parallel? FG sine theta? I'm hearing lots of sine, but it's going to be FG times the sine, right? Or you can just take it as mg sine theta. Either way is fine. So this is FF is equal to, I'm going to write this as mg sine theta. Is that okay with everybody? Okay. You know the mass? It was 0.45. Theta is 25 degrees. So then you can find FF. I don't know if we've gotten a solution for that yet. Does anybody have an FF? 1.8 something or 1.9-ish? And now, if you know FF is 1.9 and you know FN is 4.0, we can find mu, can't we? Mu is FF divided by FN. So that's 1.9 newtons divided by 4.0 newtons. Gives you a value of 0.48, 0.47. Depends on if you round it or not.
0.475.
Okay. Oop. I think it depends on if you round early or late. I have in my notes 0.47. I think that was from the unrounded. Either way would probably be okay as long as I can tell that you did good physics. That's what I'm really looking for. And no units. I was about to ask, what are the units of mu? But he got ahead of me, right? No units. So you just put a box around the 0.47 and boom, you're there.
What does this mu? I'm still confused on why we need mu. Like, what does it tell us?
So mu is just saying like how slippery or sticky two surfaces are relative to one another. So like if you're walking with your hiking boots through grass, the mu would be close to 1. Okay? It's on a scale of 0 to 1.
Yeah.
Yes. In your book, it gives you a list of like lots of different surfaces together. Okay? You don't have to memorize them. On a problem, it will always either ask you to find it, or it will say the coefficient of friction is blah blah blah. That's the two situations. So you're not ever going to have to memorize any of them, right? If you walk with your fancy dress dance shoes on ice, the coefficient of friction is going to be very, very close to what? 0, right? It's going to be probably like 0.03 or something like that. Like, oh, be very careful, right? Like, that's not a good plan.
In the book, it had some of them were just a line. Like,
It means that they aren't two things that would go together. Yeah. Right. Yes. for example. Okay. Are you guys doing okay so far? If you have a question? Guys, can you be quiet so I can hear the question?
If we have mu, and we're trying to find FF, do we
Uh-huh.
just use the other equation we wrote down?
It's the same equation.
Yeah.
So you're just going to take mu times FF.
Okay.
And that gives you FF. Yeah, yeah. No, perfect. Good question. Okay. What other questions do you have right now? Okay. This is what I would like you to do. We have about 5 minutes. I first of all want to say thank you so much for working through this patiently with me. This is a lot of stuff, right? We did a lot today. It's really, really good. On Monday, you're going to do what? You're going to bring what?
Candy bar.
You're going to bring a candy bar or similar. You're going to bring something that's in a wrapper, okay? Make sure you remember that, because if you don't, you can't do the lab, and that would be a sad deal. What I want you to do right now, because we're going to do more of this kind of thing on Monday in our lab. You have got 5 minutes. I want you right now to take a look at your homework and to look at questions 28 and 29 and get started on them, okay? I am also, guys, listen carefully. I am also going to hand out the problem set for chapter 4. You have all of the knowledge to do this. So if you have a nice free weekend and you want to just pound it out, now that you know how to do this stuff, do that. But it is not due next time, okay? It will probably, I'm not sure when it's going to be due, probably on, I don't know, maybe not Wednesday. I'm not positive. But if you want to start it, go ahead and get started. Does that make sense? Okay? But right now you've got a few minutes. Grab a book if you need to. Work on 28 and 29. Talk to your neighbors and help each other out on them, okay? Go, go, go.